All right. Good morning, folks. Hopefully, everyone had a good weekend and was able to get some rest over the weekend. What I'd like to do then is I'd like to continue on with our discussion of liquids. I want to finish up with our discussion of the one property that we talked about on Friday, evaporation, and then continue on with the discussion of vapor pressure and hopefully try to work in boiling point today as well. So I want to try to get done with liquids if we can today. If not, we'll wrap things up tomorrow and then start solids and hopefully try to finish up with this chapter by tomorrow, at the end of the lesson tomorrow. Solids will go pretty quickly, I think. I think there's a few things we'll talk about in solids. I'm going to pass over the discussion of the structure, a detailed structure of solids. That's pretty well beyond the level of this class. But I do want to touch upon that, and then hopefully start chapter 14 on Wednesday. I was thinking, I had mentioned last week that I'd like to try to get together with you folks sometime this week, and I was thinking maybe Friday we can do a live Zoom meeting. I will keep you posted on that. We'll see how things work, and then I'll keep you posted on it. But there have been some questions about when the next exam is going to be, and I remember the exam, the next exam will be on both chapter 13 and 14. I'd like to get done with chapter 14. Chapter 14 will go fairly quickly. There'll be calculations in it, but I think they'll be pretty simple calculations. And so the next exam, and I think there will be probably the last exam for our class. I'm sorry, apart from the final. I'll talk about the final a little bit more, hopefully on Friday. But that'll be the last class exam for this semester, and then the final, like I said, we'll talk about it hopefully on Friday. If we don't meet live, then I will talk about it on our video recording, and then we'll take it from there. Okay. All right. So with that said, then please let me know how things are going. Email me. Let me know if you have any questions or concerns about the direction we're going to go in the remainder of this semester, and then we'll take it from there. Okay. All right, so let me ask you to do this, folks. Let me ask you to consider this questionnaire. So number 10 in your problem set is made up of three different parts, okay? Three different parts, three different questions that I wanted to ask you in that problem set, number 10 for your problem set. We did the first one already. Okay, we did the first one, and that allowed us to kind of review kinetic energy and its relationship to movement and gases. What I'd like you to do here is let's take the second question, the second part of number 10 here, and I want you to consider this. We'll talk about this in just a moment, but we discussed what evaporation was. We said that evaporation is the process by which a liquid becomes a gas, the process of vaporization. And there's two ways that gases can vaporize. Gas can vaporize by evaporation, or it can vaporize by boiling. We'll talk about boiling, like I said, today. But we talked about evaporation on Friday. We said that evaporation occurs as the liquid becomes more of a gas. Okay? And so we started talking about how that could happen at the molecular level. At the very small molecular level, we started to talk about how that could happen. I want to pick up with that in just a moment. But we know what the relationship then between temperature and kinetic energy is going to be. We already talked about that. We said then that there's a direct relationship between the temperature on the Kelvin scale and kinetic energy. If we know then that evaporation involves the moving particles, that the moving liquid particles, if we know that, I want you to take about 2 minutes to explain then what do you think is the relationship between temperature and evaporation. So if we increase the temperature, we know the evaporation is going to increase. So I'd like you to try to explain why that is the case. It's take about a couple minutes. Write that down on your paper, and then what I'd like you to do then is have that paper in front of you as we continue and we start talking about this. Let's see how well your answer compared to what we get here in lecture, and then we'll take from there. Okay. So what I'd like you to do right now, take about minute, 2 minutes. Write down your explanation for why, as you increase the temperature, the evaporation rate, the evaporation rate increases as well. Okay, a couple minutes. Go ahead and get started on that. All right, let's go ahead then. So hold on to your answer right here. Hold on to your answer, and let's and then we'll talk about it in just a moment. Okay, but let's go ahead and let's pick up where we left off with on Friday. Just as a quick review, we said then that evaporation is a process by which liquids vaporize. The vaporization process is the process by which liquids are converted into gases. Now, this occurs both at a macroscopic level, which we see here. We take a body of water, you put it in the desert, that water is going to be gone. Okay, and we know when it is gone. It just doesn't disappear, it doesn't just go away, but it changes its state. We know that from common experience. We know that from what we learned in lower level science classes in junior high. We know then that this liquid here, this water here, will evaporate in the desert because it is being converted into water vapor. That's the process by which we refer to as vaporization. But vaporization, there's two types. Like I said, you can talk about the liquid transitioning into the gas state when we are discussing evaporation, but boiling also. And whenever we boil water at home, you've seen this, Kim. Whenever you boil water at home, the liquid state evaporates. The liquid state vaporizes, and it becomes the gas. And so if you keep boiling, eventually that water's gone as well, and so that water vaporizes. So vaporization can occur. So when we talk about vaporizations, there's two types of vaporizations. I guess you can talk about. We can mention the process by which we refer to as evaporation, and the process by which we refer to as boiling. Okay, so we need to be able to differentiate between those two because they are different. They are different ways that liquids vaporize. And so we'll talk about the boiling in just a moment. But with evaporation then, the evaporation then is when a liquid vaporizes. Okay? But we know then that evaporation occurs more slowly. It occurs slowly. It occurs more slowly than boiling. So we take a pot full of water, we set it in the desert. Okay, it will eventually be gone. It will eventually evaporate, but it's going to take a while, even in the desert. However, we take that same pot of water and we boil it. It'll be gone in a matter of minutes if we have enough heat applied to it. Okay, so the evaporative process versus the boiling process is the difference is in terms of the heat energy that you apply to it. That is the amount of heat that you put in, and also because of that, how long it takes. Okay, so liquids, the conversion here from liquids to gases when a liquid is not boiling. Okay, so we're not applying as much heat, okay, as when we boil. Okay, so let's go ahead and let's take a look at where we left off with. So remember, we talked about how with so when you heat up a liquid, okay, when you heat up a liquid, okay, you're increasing its temperature. Okay, you're increasing temperature. That's how we know that that the liquid is heating up. That's at the macroscopic level. Okay. At the microscopic level, we know then that there is this relationship between. We know that there's this relationship between, and we talked about it, temperature and kinetic energy, which means that heat is related to kinetic energy. Okay, so as you increase the temperature, we know then that you increase the kinetic energy. Why? Because you're increasing the heat, so you're increasing the kinetic energy. Okay, so as you increase the heat energy, you're going to observe then the temperature will go up, and in both cases, then what it is indicating is that the kinetic energy is going up. So this is at the macroscopic. We can observe this. We can look at the temperature. We can look at a thermometer, and we know that the temperature is increasing. Okay? And as that temperature increases, we know that at the microscopic level, this is what's happening. The particles are increasing the kinetic energy. So on the microscopic level, then, as we increase microscopic, okay, as we increase the temperature, the heat's going up, and as the heat goes up, again, this is at the microscopic level here. This is what we can observe. This we cannot observe. Okay, so how does this affect vaporization? Okay, so water initially evaporates water evaporates slowly. Okay, so we know that water evaporates fairly slowly. Okay, because the temperature is fairly low. Okay, the temperature is fairly low. So as we increase the temperature, then the water starts to evaporate faster. Now, why is that? Okay? Well, we talked about this also on Friday. Water then, liquids in general, and I'm going to use water as my as an example as we go out throughout this discussion. Okay? So liquids in general are different from gases in that they have these attractions for one another as they move around. Like we said on last week, okay, when I introduced liquids to you, how liquids are similar to gas is that the gas particles and the liquid particles are in constant random rapid motion at the microscopic level. They're moving around at all times, and they're moving very fast, and they're moving in a random manner. Now, the difference in their motion then is that gas particles move a lot faster than liquid particles, but both do move. That's how we explain then that gases and liquid particles flow. The flowing nature of liquids and gases are based upon the movement of these gas particles. So they undergo this translational motion that we talked about last week. They move from point A to point B. Okay, but as they move, though, and the key difference here between gases and liquids, that as they move, the attractions between these liquid particles basically try to hold them in place. So there's two different things that are trying to go on here. The liquid particles want to move, but then these particles, these liquid particles, are also trying to be held in place by these attractions. We talked about what these attractions are back in chapter 8. We talked about the London dispersion force. We talked about dipole interactions. We talked about hydrogen bonding. So these three interactions, these three attractions here are trying to hold these liquid particles in place. Okay, so that's the dynamics. That's what's happening at the microscopic level with liquids. Now, with gases, understand these attractions are still there, but we assume then that the attractions are so they have a minimal influence on these particles because the gas particles are moving so fast. Okay, so I will get back to that point, so make sure you keep that in mind. I will get back to that point when we get to chapter 14, and we talked about the ideal state of gases. What is this ideal? What are these ideal gases? Okay, so we'll talk about that when we get to chapter 14. But with liquids, though, these attractions, because the liquid particles don't move as quickly, okay, these attractions are going to be important. Okay, so why do we mention that here? Okay, so let's take a look at what's happening at the surface level here. So these molecules, then, okay, they will be these particles, then they will be moving around. Okay, and as they move around, they have kinetic energy. So you can imagine then that these particles at the surface here, at the surface of the liquid, okay, these particles here are being held in place. Okay? However, every once in a while, if there is a liquid particle that moves fast enough, and it's moving fast, and it's able to break free this attraction there. If it can break that attraction right there, then there's nothing to hold it in place. Okay? There's nothing to hold it in place, and it flies out. It breaks its attractions. It no longer has these interactions with the particles around it. It becomes then it becomes then a particle that has no interactions, okay? No attractions with with other particles, and we define a gas. Then remember we talked about a gas as a particle a particle in which it has no attractions with other particles around it. And so therefore, at this point here, the liquid particle, this particle here that used to have attractions and used to be part of this liquid, is no longer part of the liquid, and it's flying free. And so now it has become a gas. And so it's at that point right there that the liquid particle has become a gas. And we said then, and I reviewed this for you, we ended with this on Friday. Vapors, then at that point, then the liquid particle has just become a vapor. That's the process of vaporization at the microscopic level. Okay, so that's what we see there. Okay, so what has to happen then is that these liquid particles must have enough kinetic energy first of all. So when they go through, they must have enough kinetic energy to break free. But once they break free, they now become a gas particle. Okay? So let's go ahead then and let's continue. So that's where we left off with. Okay? So this process of evaporation, and I have it here, I have it drawn out here for you. This process of evaporation involves particles at the surface, folks, and that's going to be the key difference between evaporation and boiling. With evaporation, then, it's molecules at the surface that vaporize. It's molecules of particles at the surface here that vaporize. They acquire enough kinetic energy, and they have to break free. Now, if they don't have enough kinetic energy, that means as you lower the temperature, okay, if they don't have enough kinetic energy, they will not be able to break free. Now, does that mean evaporation stops? No, not necessarily. It depends on the temperature, okay? But it does slow down quite a bit. Why? Because the particles that don't have enough energy to break free. Just imagine this. If you take a pot, that our pot of water again, example, okay, and you set it in the desert, you take it to Death Valley, and then you compare that to taking that pot of water and putting it in your refrigerator. Now, in both cases, then the water will still be liquid, okay, and in both cases, then the evaporation will occur. But if you observe what happens with the pot of water in Death Valley, that pot of water, and again, you're not heating it up with a flame. You're not heating it up in any other way except for using the heat in the environment. Okay, because then the pot of water is exposed to more heat in Death Valley, it's going to evaporate much faster than if you take a look at it when compared to the pot of water that's sitting in your refrigerator. Now understand that pot of water in your refrigerator is not frozen yet. So we're not talking about the solid state. We're talking about the liquid state in both cases. In both cases, then evaporation will occur. But obviously, then the evaporation that occurs with the pot of water in your refrigerator versus the pot of water in Death Valley will be much slower. The key difference then is that the particles at the surface, particles at the surface in the water in the desert has much more kinetic energy than the pot of water and then the particles on the surface of the pot of water in your refrigerator. Okay, so the key then with evaporation is that the evaporation, the vaporization occurs at the surface. Okay, so with evaporation, vaporization occurs at the surface. Okay? And so that's what you want to make sure you keep in mind, because that's going to be the key difference between evaporation and boiling. Okay? So, well, like we just said then, as you start to heat, as you continue to heat, if you add more heat, if you take that pot of water outside to room temperature in your house, that pot of water is going to evaporate faster as well. So as you start to increase the heat, what we're going to start seeing then is that we're going to have more and more particles. And I'll draw this here for you. We're going to have more and more particles at the surface break free. So they will move and they will break free. Okay. And as they break free, then they're going to leave. Leave room behind for more particles to evaporate. So as these particles leave, then you can imagine then the liquid level is going to drop. Okay, the liquid level is going to drop because these particles at the surface leave, and then that allows then particles underneath it to also start to gain enough kinetic energy, and once they have enough kinetic energy, they will leave. And so, how can we observe what is the macroscopic level observation of evaporation? Okay, so the macroscopic level observation, then we see the water level drop. Okay, how we can explain that then is that the particles at the surface will continue to leave. And as these particles continue to leave, particles underneath then will have an opportunity to leave. And eventually we start seeing this liquid level then drop as more and more particles leave. So there then we've made the connection between a macroscopic observation for evaporation with a microscopic explanation. So on the macroscopic level, we see the liquid level drop. On a microscopic level, it's the particles that are leaving then that causes that liquid level to drop. Okay, so that's how we can we can connect the observation with an explanation. Okay, and so as we heat it up, the liquid, not to boiling here now, not to boiling, and I'm sorry, what I've done here then is I've shown you boiling, and we'll talk about how we know this is boiling in just a moment. Okay, but there's a key observable event that helps us to distinguish between boiling and evaporation. Okay, but what we notice then is that the liquid level drops, and as we heat it, that liquid level drops faster. So imagine this: if we have our pot of water in the desert, pot of water in the refrigerator, the level of the liquid level is going to, we're going to see that liquid level drop much more quickly. We can observe that much more quickly in the desert than we can with the refrigerator. Okay, and the explanation for that again is that these these liquid particles here in the desert will have much more kinetic energy than the particles in the refrigerator. So that then answers our question that we started out with. I started out by asking you then, how does increasing the temperature on a liquid increase its kinetic energy and thus the evaporation? Why does evaporation increase with increasing temperature? The kinetic energy, and so here's our answer. Heating increases the number of particles at the surface now. And remember, these are particles at the surface that will have enough kinetic energy to break free. So compare this to what you wrote, folks. So did you, in your answer, address both the macroscopic and the microscopic? Okay? Did you address what you could observe? Okay? Did you address the observable event of evaporation and the observable event of evaporation as reheated? And then were you able to explain that on a microscopic level? Okay, so look at your answer. Okay, look at your answer and compare it to what we just said. Okay, so make sure you can include that. So include in your answer what you could observe, the phenomenon of evaporation, but be able to explain that phenomenon at the microscopic level here. And so let's go ahead and recap before we continue on. Heating increases evaporation because it increases the number of particles with enough kinetic energy to break free. And as a result, we can observe the liquid level dropping. Okay, so make sure you write that down and make sure you compare that and make sure you write that down and then submit it today. Okay, so make sure you have your answer and the answer that we came up with in lecture here. And in both, hopefully, you have the macroscopic level observation included, as well as a microscopic level explanation for that observable event. Okay. All right, so very good, folks. So go ahead and make sure you write that down, and you'll submit that today. Okay, and so let's continue on then. Let me just finish up by saying here then that the paradox of evaporation is that it requires heat. Evaporation requires heat. Obviously, if there's not enough heat energy, the particles don't have enough kinetic energy, and so the particles at the surface can't break free. However, and we'll pick up with this tomorrow, evaporation is actually a process by which the ambient, the temperature around the heat and the temperature around the liquid actually drops. It drops because evaporation cools down the environment. Okay, it cools down the area around the liquid. So what we're going to do tomorrow then is we'll continue with this discussion of evaporation. We'll talk about how evaporation is actually a cooling process. Okay, all right. So with that said, then please make sure you submit your answer for today. Okay, and then folks, I will see you tomorrow. If you have any questions, stop by today after school, 1:30 to 2:30, and I'll see you folks either then or I'll see you folks tomorrow in lunch. Okay, have a good day, folks.